because the temperature plays a very important role. So this is also very important. We have with us Professor Dr. Babita. She's assistant professor of physics in the School of Basics and Applied Sciences, Jetali Zone at Neemrana, Rajasthan. He is PhD in physics and worked at National Physical Laboratory, New Delhi, which is NMI of India. Right now, she is in the Academy of Scientific and Innovation Research, and her previous title was Optimization of Thermal Parameters for Acoustic Gas Meters. She has written large number of research papers, and she's teaching the students, preparing the students for the examinations and the PhDs, etc. Thank you very much, ma'am, for accepting our request and delivering a lecture on this very important topic, which is not only important for the laboratory's point of view, for the country point of view. Thank you very much, ma'am. We have with us our Honorable Shri B.N. Dixit, our Director Legal Metallurgy, sir. Sir, kindly speak two words so that we can also benefit from your kind words. Over to you, sir, please.
Thank you, Astosh, Dr. Astosh, Director Legal Metrology, Government of India. Dr. Babita, Assistant Professor in Physics. And today the chief guest and speaker of the program. This is the continuous series of the Saturday program. Very good series, and different topics are being selected on every Saturday for the scientists who are participating in this very program to know the different knowledge on the different subject and all those very things. Temperature is the one of the base units given in the Legal Metrology Act 2009. So that is very important point that this is maintained at the National Physical Laboratory, RRSL, Secondary Standard Laboratory and Working Standard Laboratories. So in spite of chemical measurement and other type of things where the physical measurement is also very important, because when the accreditation point of view you are going to different laboratories, then the atmospheric temperatures are being measurement in every laboratory and that very temperature is being maintained. For that the standards thermometers are being used, which is kept in the every laboratories. Those things are being calibrated to the one of the higher laboratories are in national physics, particularly in legal metrology. It is calibrated in the National Physical Laboratory. So that point of view, it is very important thing. And when we are going for the chemical measurement, then there are the melting temperature, boiling temperature, and so many other type of things are there. So when the tests are being done in the laboratory, so the various temperature plays the very important role in the various measurements. So today I hope that Dr. Bhavita will give the nice lecture and will provide the good knowledge to us so that we will be aware about some more uh, things or instrument which we have not been heard about, that we are expecting something new from her, that the audience and the scientists and the legal metrology officers may knew about that. So I request to continue the seminars, and now the Ashutosh Agarwal will, Director Ashutosh Agarwal will request Dr. Babita to give her lecture. Thank you, Ashutosh ji. Thank you, Dr. Babita.
Sir, thank you very much, sir. Thank you very much for your kind and motivating words. Thank you very much. We are always looking towards you for the motivating words, sir. I was just looking Dr. Babita's CV, sir. She is, she has done about 25 years after I completed my MSc in physics, long back. Over to you, ma'am. Please. Thank you very much. Thank you. Thank you, ma'am. Please. Your mic is off. Your mic is off, ma'am. Atul ji, am I audible, Atul ji?
Yes, sir, you are audible, sir.
So kindly check her mobile. Her mic is now off. She's not able to, I think, unmute herself.
Yeah, now it's fine. Yeah.
Now audible. Thank you. Please, over to you, ma'am. Please.
Yeah, thank you so much, sir. And a very good morning to all of you. So, shall we start, sir? Okay,
Please, ma'am.
So, a very good morning to I would like to today and I got a opportunity. So, the topic of quality. As mentioned, SRNPS in the quality infrastructure, commitment to bring the recommended ISO and IEC, which means my PhD just was based on at
I'm sorry, ma'am. I'm sorry. Sorry, ma'am, for interrupting you. Ma'am, your voice is breaking. So kindly switch off your camera and then speak. Maybe due to the signals. Voice was. Yeah. Please. Continue.
accurate temperature measurement is required in every field, like temperature metrology having a great impact in space science, high energy physics, and in medical. And in the COVID time, we all have important the IR sensors and thermal imaging in the temperature measurement. So, everywhere in every context, we know that temperature measurement is very important, and that is why it is important to standardize and calibration of every equipment that temperature measurement. And even temperature and humidity standard of CSL NPL is a major contribution in preservation of the Constitution of India. The humidity inside the chamber was calibrated by the Constitution like temperature, and which maintained the humidity of the Constitution of India. That's why we can say that like it's maintaining the Constitution of India as from the scientific purpose. So temperature metrology having a great impact here. The temperature measurement calibration facility is provided between temperature minus 200 degrees Celsius for the SPRTs, TDs, thermocouples, and radiation thermometers, thermal imagers, and blackboard. And these are all sensors different application in different areas. So this is the historical background towards the temperature meteorology developments. Temperature is the measure of the average kinetic energy, as like the first measurement were done by the scientist Galen in AD 170, and it was defined in terms of the ice point, zero temperature we have taken at the reference point. But in 1954, triple was came under consideration. But the story behind this topic, like why we are developing the primary standard at NPL India for the new primary standard, if we will talk earlier, the definition was based on the triple point of water. And in 2005, it was decided, okay, everywhere the water consistency and the isotopic composition are different is different. So it was decided that Vienna standard mean ocean water will be taken as the standard water for the isotopic composition. But as we are the human beings, so there must be some like uncertainty parameter, which will be contributed everywhere during measurement of the isotoping composition. So to remove the material property in 2011, it was decided that water will be material dependent property, or we can see that triple point of water dependent property will be removed, and we will redefine the Kelvin in terms of the fundamental concept. So here the evolution of temperature measurement scale. So earlier it was defined as the ice point of water at the fixed point, and we have taken it as a reference point for the measurement of any temperature. And in the 10th CGPM meeting, the 10th CGPM, which is the General Conference of Weight and Measurement meeting, which held in 1954, it was decided that triple point of water will be taken at the fundamental fixed point, and the value of that will be 273.16 Kelvin. In the IPTS 1668, triple point of water was replaced with the ice point, which was defined in the in the earlier stage. So in ITS 90 International Temperature Scale, there were few fixed point of temperature is defined in this document of International Temperature Scale, which was defined in 1990, and we listed out few fixed point as we have taken like during the calibration process that we used in our laboratory. But later on in 2005, because people use triple point of water as a reference point, but everywhere, if you are taking the measurement from the Delhi water or from the Rewari water or from the Rajasthan water, so the isotoping composition will be different. And there are hydrogen isotopes. So it was decided that the Vienna Standard Mean Ocean water will be taken as the standard water in 2005, and then in 2011 by CCT, the Consultative Committee of Thermo defined it as the we will redefine the Kelvin in terms of environmental constant, and by using that theory, gas theory, it was decided that kinetic energy is related to the gas to the temperature as by the relation A is equal to kT. So there we can use the fundamental constant K as the fundamental constant for the redefinition of the Kelvin. So from 2017 core data values in November 2018, it was redefined in terms of Boltzmann constant, and from the May 2019 onward, it was implemented practically. So earlier, this was the triple point of order, which was the primary standard at CSI NPL or in other laboratories, which for the different countries like primary standard. But after that, this is the primary standard in other countries. At NPL India also, we are developing the primary standard, which is based on the fundamental constant weight definition. But actually, we are still working on that. It is under the development process in our laboratory. And I'll explain in the next slides how much work we have done. So this is the gas theory, which is relating the energy and temperature with their fundamental constant, with the Boltzmann constant. And this fundamental constant will be used as a for the redefinition of the Kelvin. So earlier, WCL was the primary standard, and now the gas, like the earlier slide I've shown, this cavity will be used as a primary standard, but we need lots of isolation for this cavity, which will be explained in the next few slides. So, what are primary thermometry standards? So, primary thermometry is the measurement of thermal temperature directly without calibration against any other more accurate thermometer. So, these are the from the last few decades. These are the different thermometry methods which were developed in different National Meteorology Institute internationally. So, there were few criteria that need to be fulfilled by these methods. Only then it will be considered in 2017 CODATA value. So here we can see the acoustic gas thermometry methods, dielectric constant gas thermometry, and Johnson's noise thermometry are having the major contribution and fulfilling the criteria of the uncertainty of 1 ppm. So that's why we have considered the green color belt we have seen. These are the three methods which are contributing majorly. So internationally, these three methods were considered for the primary thermometry methods. So these are the CODATA summary, which is like from the 1975 to 2017. So from the 2017 CODATA, the redefinition of Kelvin was take place, and by fixing the value of Boltzmann constant and taking the uncertainty at 0. So earlier there was a problem because the definition was depending on the triple point of water, and this was a favorable point. And the isotopic composition of water is place to place. Now it is independent from the material. So in the 26th CJPM meeting, which was held on 16th November 2018, we have fixed the numerical value of the Boltzmann constant, and the unit of thermodynamic temperature, Kelvin, was redefined. And the new definition is defined as the by giving the fixed numerical value of the Boltzmann constant as 1.380649 into 10 to the power minus 23 when it is and in terms of the 7 SI units, it will be kilogram meter square per second per Kelvin. And these all these units are having their own standards, which is dependent on some fundamental constant. So now we are having the thermodynamic temperature and international temperature scale 1990, which was defined. So this is the difference. So near about the point of triple point of water, we can see the uncertainty is not so much. But as we go away from the triple point of water, the uncertainty value is increasing. And the difference between the T minus T90 is increasing. So to remove this uncertainty, we have redefined and we are not giving any favorable to any particular fixed point. So what will happen after implication of the redefinition of the Kelvin? We can directly do the realization of primary thermometry, and this redefinition is particularly best beneficiary for 20 Kelvin and temperature above 1300 Kelvin, because in between this range, which is near the triple point of water, which is not going to affect so much, but above that and lower this particular temperature range, of course, it's going to affect much because the uncertainty propagation is more. Now the new definition is dependent of any material, so we are not having any favorable fixed point, and we are not going to favor any measurement methods. There is no error propagation from triple point of water. Because earlier it was necessary to take the triple point of water as the reference point, so it was like error was propagating as we go away from the triple point of water. There will be no immediate impact on the status of international temperature scale 1990 and provisionally low temperature scale which was defined in 2000, but later maybe we redefine all these temperature scales. So this is the Meissen party. So this Meissen party is the CCT documents which will define the definition of SI units of temperatures and its definitions and the methodologies that we are going to use for the redefinition process. So we are having the primary thermometry methods and then absolute and relative thermometry and temperature range block 20 Kelvin to above 1300 Kelvin. So these are the changes that we are going to do in this document after redefinition of the SI. So at NPL India, as I mentioned in my earlier slide, there are lots of methods that we are going to use for the development, but three methods having the major. This is a dielectric constant gas thermometry, and Johnson's noise thermometry. All these methods are relating to measurements with the air of speed of, or we can say that it is relating the kinetic theory of gases with the some parameter. So here we can, in acoustic, the name is relating acoustic. So which is related to the speed of sound. Which is relating the kinetic energy, the speed of sound. So that's why we are having the name AGT. In the same, we are in DCGT we are having the dielectric constant. In Johnson's noise thermometer, there is some different. So these are having different principles. But the thing is that why we are using a thermometer at NPL. So internationally, in 2017, different data values are there. But we can see that from the table also, in 2017 co-data value, the acoustic gas thermometry having the minimum contribution in the uncertainty measurement. And that's why by following the co-data from the last few years and at NPL India since 2014, we are developing the acoustic gas thermometry methods and we are earlier labs also. And from the latest survey and from the past history of the acoustic gas thermometry, we have chosen the acoustic thermometry development. So acoustic thermometry is one of the primary thermometry methods which are contributed in the realization, which is based on the Boltzmann constant. So the uncertainty is below 1 ppm, and we fix the value of the Boltzmann constant at 1.380649 into 10 to the power minus 23 joule per Kelvin, and with the zero uncertainty. These 2017 co-data values. So these are the list of NMIs which this acoustic gas thermometry method, and having the different shapes of the resonator and the different size and material and the gas. In the case we use the inert gas, either or we specifically use we need the copper. There are parameters of the reflection for the microwave and acoustic, so that's why we polish for acoustic. And these are the radii that use these radii resonate cavity alignment. We are supposed in the triplet formation. If we will not take the perfect, there is overlapping, we will not get the triplet. So that's why we need a little orientation in the cell. This Excel ellipse, which is choosing the gas as R. The list of NMIs which given the value of K as this one with the parameter in dimension, mass, temperature, contribution. This fixed point. So the principle of acoustic gas thermometry. So acoustic gas thermometry is based on the sound in a gas medium inside a cavity at different temperature at a constant pressure. We all aware about this thing. This is the fundamental principle of physics that with a variation in pressure or temperature, there is a variation in speed of sound. So here we can see that this Boltzmann constant is relating the speed of sound and temperature. So this is the equation which is relating the Boltzmann constant to the speed of sound and temperature. So here if we fix that pressure, then we will measure the speed of sound. Then again we fix the value of pressure, measure the speed of sound at a particular temperature, and we extrapolate the equation, we will get the value of the temperature. So first measurement will be by keeping the temperature fixed, and we will keep varying the pressure, and then we will find out the value of u here, and we will find out the value of the Boltzmann constant. So first measurement will be taken at triple point of water to make the consistency with the earlier definition. So this is the setup like that we are going to use. So this is the cavity. It seems like in this way. Here is the cavity. So here are few post two plugs for the gases, like for gas input and gas output, and two plugs for the microwave input and microwave output, and four plugs for the capsule SPRT that I'll explain next few slides, that we are going to insert in this cavity for the measurement of thermodynamic temperature. So this is the resonator cavity, and this is the pressure vessel, and then the pressure, and the whole assembly will go into a highly stable temperature bar. So this is the determination of the Boltzmann constant. First of all, we will determine the Boltzmann constant by using these equations, because as I mentioned in earlier slide that we are going to use the microwave as well as acoustic probe. So microwave probes, we are going to measure dimension of the cavity simultaneously, because we are assuming that there might be some minor changes in the cavity dimension while doing the measurement. Acoustic measurement we are doing because we have to measure the variation in the speed of sound with the variation in the temperature or pressure. So we are going to take both the measurements simultaneously, and this is the formula which is relating the Boltzmann constant to this microwave and acoustic values and the speed of sound. So now we are having have to first of all we fix the value of the Boltzmann constant by taking the value of triple point of order with the earlier definition we just made it, and we just fix the value of Boltzmann constant with the zero uncertainty, and then we will start measuring the temperature. So in the thermodynamic temperature measurement, we are having two opportunities. Either we will take the measurement at some random temperature by using the same formula, which is absolute measurement, and the relative measurement we are having the thermodynamic temperature measurement. So in the absolute measurement, what we will do, we will take the measurement at triple point of water, and then we will take the measurement and some unknown temperature. The speed of sound should be at triple point of water and triple point of at some different temperature. So by taking the ratio, because all the other parameters will be same, there will be difference in the speed of sound at triple point of water and at some unknown temperature, and then we can calculate the unknown temperature directly. So this is the relative method. So now, what is the experimental procedure like for the development of acoustic gas thermometry? So first of all, we need to design and fabricate the resonator and then we will do the dimension measurement of the resonator and by using the coordinate measurement machine and determination of the pattern of the microwave resonance. And then we will optimize the thermal pressure and gas flow parameters and we'll do the measurement of velocity of sound by acoustic and microwave measurement at triple pint of water by varying gas pressure. And then in correction and the uncertainty budget we will measure for all these parameters and then we will rely the new definition which is based on the Boltzmann constant and then measurement of the thermometer temperature will be done. These are the absolute methods and then in relative method what we will do? We will do the after this we will calculate the value of speed of sound at the triple point water and then by taking the ratio we will measure the unknown temperature. Then we will estimate the T minus 90. So here, this is the formula which we mentioned here. Here we can say there is contribution because of the thermal part, because of the dimension part, because of the pressure and flow, and because of the acoustic, and because of the way gas. So these are the parameters which will contribute in the uncertainty for the determination of K. So here we can see that the contribution because of MI is the 30% weightage and then because of the temperature is 26.1% and because of the speed is 43.6% and because of the fundamental constant that is used in the equation is 0.4%. So here we can see that because of this temperature contribution is 26% and the most of the measurement part will be initially we needed to be done. So in this temperature measurement, what are the parameters which contributes? First of all, is the point of order because we are going to take the first measurement. And, hello, my voice. My voice is clear, sir. My voice is clear, sir.
Yes, ma'am. Now it is clear. Please continue.
Okay. Okay. Sure.
तो पहले साल में 12 महीने बाद के बाद
So these are the parameters which are contributing. So here we can say that because of the temperature, on the list of parameters, like first of all the realization of triple pint of water, and then temperature calibration. Because we are going to use 4 capsule SPRTs for the thermal mapping, and then breeze reading, gas temperature, correction in triple pint of water, self-heating correction, standard resistance stability. These are the parameters which is majorly contribute in the this T part. We can get the like optimization of thermal parameters, which is the part. These are the major contribution because of the thermometry. So these are the thermal optimization part. In the first one, like as I mentioned in the earlier slide also, design and fabrication of the resonator assembly, which I'll explain in next few slides. And in the thermal optimization parts, we are having the improvement of CMC because in 2007, the CMC at CSI LPL was defined, which was 0.17, and we improved it as 0.26 milligauge. So first of all, we have done because at that time, 2007, we were not having a particular cell. So in that type of cell, we were not having the isotopic composition is not. So we used now we are having the fluke cells. The isotopic composition is also known. And then heating effect correction is having the major contribution because sometimes the heating of the measurements. So that's why it is important to consider the heating effect correction. And then we are having the standardization of 4 capsule SPRT that we are going to use for the thermal mapping of the resonator. And then stability and uniformity of the large temperature bar. So here is the first of all we will cover the part of design and fabrication of the resonator assembly. So this is the resonator assembly. Why we are calling resonator assembly? Because this is the resonator, and for this resonator, we need an isolated environment by the way of pressure or temperature. So we want a particular environment for this resonator. So here is the pressure vector, and then here the vacuum pressure. So vacuum vessel will protect it from outside variation in the temperature or pressure, and then there is pressure vessel will keep the pressure of this cavity, and this pressure vessel is almost same because we just wants to prevent the leakage of the gas through this cavity. So the cavity is having the dimension, inner dimension is 10 centimeter and outer dimension 16 centimeter. And then according to this size, we have designed the pressure vessel and vacuum vessel dimension. And then we are going to insert 4 capsule aspirates and 2 probes for the microwave and 2 probes for the in this cavity. And we are going to uh, inside this whole assembly. This is the whole assembly, 3D view of this assembly. Inside the high stable bath that we will explain in next few slide. So the standardization of that the bath is also important. So for this cavity, we are going to use the highly, like we can say that oxygen-free high conductivity copper, and resonator shape is also spherical cavity. Which is joined by using 2 hemispheres, and the dimension is 10 centimeter, the inner cavity dimension, and outer is 16 centimeter. And the gas we are going to use is the argon gas, which is highly pure argon gas. Either we have 16 or 7 purity level of the gas, and the gas pressure is up to 10 bar. And then the requirement is like a mirror by diamond turning, because the reflection of the microwave and acoustic rays, we want the maximum reflection of that, because we don't want any absorption from the wall of this cavity. From that we will get the clear resonance formation, or we can say the triplet formation. So the surface roughness is of the order of 40 nanometer, and the accuracy of the radii is 0.1 mm by cm. We use the coordinate measurement machine for all these measurements. So we achieve all these criteria. So here you can see this is the fabrication of the copper coil spherical resonator. As I mentioned, this is not perfectly spherical in shape. This is quasi spherical. For some particular region, we have chosen the quasi spherical to maintain the like proper triplet formation. So here is the microwave, gas out, gas in, blank. One is like hole for the dummy. We just kept it like for the there's some problem or we need some other instance in the future. So that's why we have taken some dummy also. There are 2 dummies. One is there and one. So these are the ports. You can say, and one is this. Like we can say, this one is for the periphery temperature measurement. So we have chosen the holes for the thermal mapping in such a way that all the periphery temperature will be calculated, and we will average out for the whole ITS 90 temperature measurement, which will be done by the small capsule SPRT, like capsule size SPRTs, we can say. So this is very small in size. We are not going to large size SPRTs, or we can say ST SPRTs, and it is not easy, although it is itself is a primary thermometry methods, but it's having a huge size, and which is not possible to insert it inside a ITS 90 any triple point cell because of its size constraint. Which I will consider the size, and it will be possible. Let's see how long it will take. So the different plugs and points that we used at different angles and orientations. And here we can see at CSN NPL, this is the resonator assembly that we have used, and these are the plugs of the copper tubes, the pressure and vacuum testing, and we tested the of this resonator and achieve the level which is required. And in the coordinate measurement machine measurement, the resonator dimension was measured, and we have seen that the inner surface of its elsewhere was probed at 576 locations with a stats of theta is equal to 5.6 degrees Celsius. So we thank the Life and Emission Group of NPL India for their help and support. And this is the surface roughness, and this is the dimension of the upper top part of the hemisphere, and this is diameter of the bottom part. So here the surface roughness is 32 nanometer, and this is the certificate that we obtained after the calculation for the length and dimension. And here the installation and testing of the pressure vessel. So after that, the resonator assembly will go inside this pressure vessel because we are going to operate up to 10 bar. We just tested the pressure vessel range up to, and then the pressure vessel was filled with the argon gas, and it's yours and check the leaks. So these are the parts and accessories of this pressure vessel. And this is the installation and testing of the vacuum vessel. So we tested the vacuum up to 10 to minus 5 torr. So which we are achieved, and we use the thermomolecular pump for this testing. So these are the pictures which we have taken while testing the vacuum vessel. So this is the pressure controller. This here we can see that this is the argon gas. This is the argon gas cylinder, and we are just testing the pressure like that we are going to provide, because we have to continuously keep the flow of the argon gas while taking the measurement. So we have taken the measurement, and up to the pressure is controlled within the 12 ppm, and the measuring range is up to 0 to 15 bar or higher. So next, in the thermal optimization part, we have to improve the uncertainty of triple pint of water. So as triple pint of water, what the, like we can say this TPW side was a primary standard earlier. Before the redefinition, and now onwards also we are using this one as the primary standard, because we are not yet developed the acoustic NPL, but few NMIs are using their new primary thermometry setup. But we need to improve this triple point of water, because as I mentioned earlier, the uncertainty of triple point of water in 2017 was 0.171 millikelvin, because at that time the topic composition which was not so known to us, and now the cell that we used 3 ensemble of cells for the measurement. And now the isotopic composition of this triple point of water cells is known, and we use highly stable DC resistance thermometry bridge for the measurement of. We use two standard platinum resistance thermometers and 3 triple point of water cells, and we do the comparison. So these are the measurements that we have taken. For the repeatability, we have taken for the 16 to 17 hours measurement. We have taken for the repeatability. And for the reproducibility, we just maintain created the mold of ice, and then created the triple point of water state, and then we melted it. And again, we take measurement. Again, we created the mold, and then again created the triple point of water state. And in that way, we have taken 3 measurements for like each cell. These are the metals we prepare, like metal 1, 2, 3, and we melted it, and then again we taken the measurement. So this is for the reproducibility. And cell fitting is having a major role, because we are going to use the standard platinum resistance thermometers. And as platinum is a wire, and because of the current flow, there must be some heating effect, or of course, that is going to influence the. So that's why it is important to contribute this parameter. So here we can see that these are the slope methods we use for the determination of. So sorry, for the measurement of cell fitting effect, which is majorly contribute in the Boltzmann constant measurement, because of the optical thermal optimization of this part is having a major contribution in the uncertainty determination of triple point water cell. So here we can see that the temperature which usually like 1 milliampere and 4 milliampere for the measurement, which is identically defined in the 60 documents also for the measurement of self-fitting action. So in the in the because we all know that here is the sensor part of this thermometer, triple point of water state is existing here, and this is the ice part, and this is the liquid part, and this is the web part. So there must be some variation in the because of the heat flux immersion. So that's why we are just considering like, okay, as per point of water state is existing here. So we just put it up by varying the height from the bottom and from top, like in 2 centimeters, and then we repeat it from the bottom to top and then top to bottom, and then we'll take the measurement and just calculated the value of heat flux immersion, which is going to contribute in the uncertainty budget for the triple point of water measurement. And this is the light piping. As we know that because of the light also, there must be some effect in the measurement because when light fall on a metal, so it just varies temperature. So we are just assuming that there might be some minor variation. So whether it is going to contribute much. So, but we consider like in the few part it taken in light, and then we cover it with the black cloth, and then we have taken the measurement, and then we can say that it is not affecting so much, but we consider this effect also. So these are the correction factors that we also taken in triple point water, and why we have chosen this. Because of course, if we will not choose in the uncertainty, as I mentioned, 0.06 millikelvin we are obtaining, but here we can say that 1.73 millikelvin is the correction value that we obtain from the cell feeding. If we will not do all such kind of correction that we are obtaining from here, here we are obtaining the 0.717, here it is like the total calorie value, this one is here. So if we are not going to hydrostatic correction is chosen because of the in the bottom part we are having the sensor, and at the upper we are having the three states. So as the because of the gravity is going to affect, so we are just choosing like where the sensor part and where is the triple point of water state. So we have to consider that part also, and sulfating is having the major contribution. There is major contribution and which we need to add on, and then only we can say the uncertainty is having an important role. So this is the uncertainty measure. So these are the uncertainty parameters which we can see, which is repeatability, reproducibility, and then bridge measurement, and the standard resistance, and temperature stability of the standard resistance, and then impurities and isotopes, and hydrostatic head corrections, and garage pressure of the cell, self-heating correction, and heat flux immersion, light pipe. These are the parameters to my water cell. So these are the contribution because of that. So here we can see that like all these are of type A and type B contribution we obtained from the documents, and few we just measured in the laboratory. So now, as I mentioned in the earlier slide, that we are going to use the 3 triple point of water cell. So here in the from the 3 triple point of water cell, the uncertainty we obtained is 0.057 millikelvin and 0.06 millikelvin and 0.058 millikelvin, respectively. In the coverage factor of 2 and confidence level is 95%. So here is the list of NMIs having their external uncertainty for triple point of water at the percent level. So India is lying in this range. Now in the future, maybe we will participate in the intercomparison for the triple point of water. So now, okay, first part we have done for the triple point of water, and now capsule SPRT that we are going to use in this in the periphery of this resonator for the thermal mapping. So these are the locations where we are going to insert all the four resonator, four thermometers, which is small size capsule SPRT that we are going to use because the bulky because we need in a comparison at the ITS 90 temperature, and directly because it's a primary standard. As SPRT we are going to insert in the primary like TPW shell, but we can't insert this acoustic inside the primary standard cell. So that's why we need to calibrate these SPRT from that, and then we will measure the temperature from this cavity. So point of view that we are going to use. So these two that we are going to use at the edges of the resonator equator, and two at the top, one at the top and one at the bottom the cavity. So we are going to initially we are going to work from triple point of mercury to the melting point of gallium. So here we can see the measurement of capsule SPRT at the melting point of gallium, and the same parameter of uncertainty which we have taken in the triple point of water taken at here also, like heat flux immersion and heating effect. and these are the uncertainty budget. Similarly for the Galileo and triple point of order, and here is the uncertainty propagation for these 3 fixed points. So like we can see, this is the propagation uncertainty from the range from Mercury point, Galen point. Then in these range, we have visually measured the uncertainty, and then this is the combined external uncertainty which is going to propagate. So now why we are giving so importance to the heating effect? You can see that like this is the contact medium that we are going here we are going to insert any thermometer. So we can see from the earlier slide that at triple point water, the value of self-heating correction is 1.7 millikelvin, and the value of uncertainty is 0.06 millikelvin. If we will not add this corrected value in the measured value, then there will not be any meaning of this uncertainty, because this value is much higher than the uncertainty value. So first of all, we need to correct the value, and then we can say this is the uncertainty with the corrected value. So that's why we are having the actual value is the experimental value, and then we will use the corrected value. We are taking the minus sign because self-heating value is like increasing the temperature from the actual temperature. So that's why we are just correcting it by subtracting it from the real value. So that's why the most important parameter. We studied about the self-heating parameter in depth. So we have chosen kind of SPRDs. We can say capsule SPRD we have chosen, SPRD we have chosen, and SPRDs of different self material we have chosen. So here we can see the principle that we are going to use for the self-heating correction value. Because we know that the sensing current of SPRT cause self-heating correction, which is I square R. To add the value of resistance is increases, the self-heating correction value increases, and the value of current is increases, then also self-heating correction value is increases. So that's why there is variation in the different SPRT, because in few SPRTs are having 25 ohm resistance and few are having 100 ohm resistance. Few SPRTs we are just using the 1 milliampere current, and in fact we are using root 2 milliampere current. So that's why we have to select the criteria, like which will be the perfect criteria that we will use for that particular range. So we have chosen the SPRT 25.5 ohms. These are the list of 4 PRTs, and we have measured for the 5 different values of current. So these are the value of current for the 0.5 milliampere, and then 0.707 milliampere, then 1 milliampere, and then root 2 milliampere and milliampere. So we can see that as the value of the current is increasing, the value of resistance is increasing. So that's why we can see that, because resistance is not itself is increasing, it is increasing because we are having the same cell. We are using the triple point of cell for the measurement of this temperature, but this is happening because of the variation in the current. So we can see the resistance value is increasing, and which will be the correct value in the actual measurement. So here we are having the 2 methods that we can use, the second order polynomial field or by using the Stokes method. So we calculated and we just compared these 2 methodologies also, like from these 2 methods, what is the variation that we are obtaining, and we compared the zero current resistance for the 2 current and multi-current methods. So when we do the correction, we can use the 2 current methods or multi-current methods approach. We will calculate the value of resistance at different value of current, as we did in the capsule SPRTs and triple point of water measurement for the milliampere and root 2 milliampere. That is 2 current method approach. So here the list of sensors that we use for the study. So here we can see that in the sensor there is gas filled with either argon or helium. So we can see that the thermal conductivity is increasing. That and then we can see here is the PT 100. So PT 100, that means 100 ohm resistance we are using, and we are getting the highest value of resistance, because these 3 are having the 25 ohm resistance. So because it more the resistance, more is the, so that's why we are getting the highest correction in the PT 100. Now we need to compare these metallic SPRTs. Both are all these 3 are having the same resistances, which is 25.5 ohm. So here we can see that the value of second one is the SPRT. So SPRT is having argon gas and 0.016 and quartz with the thermal conductivity is 1.44. So here in both capsule SPRTs and SPRTs having the thermal conductivity is 1.4, but for the gas field is different, which is helium and argon. So here for the SPRT is higher because the conductivity or thermal conductivity of argon is less, so it will not dissipate the much heat, so that's why the value is high, but it will dissipate the heat, so that's why the value is low. Now the metallic, which will dissipate the more heat of the high thermal conductivity, and because of the self material which is inconel, which is also having the value as 11.2 high conductivity, so that's why we are getting the lowest value of heating here. So these are the combinations that we used for the study of the self-heating correction because of the cells that we are going to use. So here we can see that because of the ambient, in the ambient we use a thermal conducting medium. So either we can use like air or alcohol or distilled water, which depend on the experiment, which experiment we are going to do and which temperature range we are going to do. Go. If suppose if we are going to below the temperature freezing point of temperature, so of course we will use the temperature like either. So in that temperature range also we can see that the thermal conductivity decreasing, the self-heating correction value is increasing because it will not dissipate the much. Here we have also studied about the PRT is like having different winding. Everything is same, only the winding difference is there. So we are having the coil filament and then twisted glass ribbon, and then single layer filament on mica cores. So here we can say that how much part of this filament is in the contact, because the current is flowing that this wire, and how much this wire is in contact with the filament, how much heat it dissipate, how much cross section area of this filament is in touch with the quartz. So then if there is more area is in touch, there is more heat dissipation will occur. So here we can say that the self-heating correction Kelvin, and this is the uncertainty value that we are obtaining, and this is the self-heating correction is 1.37, and here it is for this one is 1.75 degree. The minimum value which we are obtaining from here. Why we are obtaining it from here? We can say this, it is winded one by one, and here it is the more contact with the encoder, so that's why more heat dissipated, more area of cross section to dissipate the heat. Here we can say that as compared to this one, is the more area is in contact because twisted in ribbon form, but this one is like passing through the holes only. So it is not having such kind of exposure that we obtained from the earlier two. So that's why the more self-heating correction value is there. We also compare the value at different temperature. So we can't say the self-heating correction value will be same for each fixed point, because of the material like we can say platinum inside the standard platinum that we are going to use. So that's why in the platinum properties also getting varied. And and then after that there is dissociation of the oxides. So up to the oxides is formed. There is we can say that up to the temperature near about 300 degrees, up to the delta T value is increasing, and the correction value is increasing, and then the oxide will get dissociate, it will regain its original form. Then it will like the resistivity value of the intrinsic property of the platinum resistance, or we can say that standard platinum will get vary, so that's why the delta T value will also start decreasing with the variation in temperature, because up to the 700 degrees Celsius it will completely dissociate. So that's why at each fixed point we need to calculate the triple we need to self-heating correction value separate. We can't assume that the self-heating correction value at triple point of mercury will be same at the triple point of water, or at the freezing point of zinc, or freezing point of aluminum, or like indium, or any other point. So that's why we need to calculate it's differently or separately, you can say. So as I mentioned, like the whole assembly, this whole assembly will go inside this large volume liquid temperature bath. So this is the alcohol bath. This is 300 liter, and we have just done the standardization of this bath from -40 degrees Celsius to 120 degrees Celsius, and these are the data for the stability, and we obtain the stability within plus minus milligauge and uniformity from plus minus 2 milligauge, because as we are working in the standard, so we have high standard for these measurements. So that's why we are just isolating this whole quality, because this resonator is the main heart of this experiment, and here we are going to take all the measurement, and then whatever outside of things we are using, we are just isolating from some other influence or some other parameters that we are contributing for the environment. So these are the uniformity, and these are the plots for the axial and uniformity that we can see it from here. So what we have done, we just chosen a area according to the periphery of this vacuum vessel, and then we inserted three different kind of we have taken the measurement for a long term, and we just see like what is the uniformity of this at particular fixed position, and then for the axial uniformity, we just change the height and we have to choose the measurement. These are the, like here we can see that we are at different height. The height, so according height of this vacuum vessel, we have chosen. So then we open the plot in such a way. We presented this work in the last conference of EdWay, which happened in the Goa. So these are the setup measurement of acoustic gas thermometry assembly, which is going to insert in the bath. And here is the different PRT that we will insert here, and we will measure the temperature stability and uniformity of this bath. And of course, at which temperature measurement we are going to use, we will set the temperature of this bath in that range only. So earlier we are going to work in the temperature range -40 degrees Celsius to 30 degrees Celsius. So we have checked the uniformity and stability of that range only. So this is the setup at CSIR NPL. This is the picture. So here is the crane like that we have developed, and here is the gas assembly setup. And this is the picture like that we are going to insert in this bath of this assembly. So this is the bath, originally high volume temperature bath, that is in our lab, and this is crane which is going to lift this whole assembly, this arrangement, and crane is movable in its direction, and it can the capacity of this crane is up to 1.4 ton, and it will keep all the assembly of acoustic gas thermometry smoothly inside this high volume temperature bath. So it will be easy and convenient for us to work on this setup. So here the summary of the acoustic at CSIR NPL that we are developing. So we are having this resonator assembly that all the acoustic instrumentary we designed and fabricated the diamond finish copper quasi spherical resonator of 50 radius, having coordinate measurement machine with the help of coordinate measurement machine. The dimension is 99.997 and then certainly 0.0011 and the surface toughness is 32 nanometer. This assembly will be placed in a pressure vessel. This is the pressure vessel, and this is the vacuum vessel. And we tested the pressure of this pressure vessel, and this vacuum vessel's vacuum is also tested in the working grain that we are going to use. And these are the capsule SPRTs. Going to use for the thermal mapping of this resonator assembly. So we have done the standardization of these capsule SPRTs. The certainty of deployment of water cell is also improved, and then we still pass on to the capsule SPRT standardization, and then this capsule SPRT will be passed on this uncertainty to the determination of the Goldman constant. This is already fixed the value in 2074 data, but still for our country we are going to develop. So first of all, we need to take the measurement, and the procedure follows. So, and all the requirements will be fulfilled. And this is the whole assembly, and we're going to use the highly stable grease for this measurement. And this whole assembly will go into this bath, and for this measurement we require 0.1 millicalipper are stability to the copper cavity and the pressure and the resonator assembly. So that's why we are going to put in this temperature path and idea. It is important to the stability of this path to be plus minus 1 millikelvin and 40 minus 2 millikelvin. So in future, we are just going to present this and acoustic and micro measurement. Radius of the resonator is estimated by using the microwave because, as I mentioned, it is important to consider each and every parameter. So simultaneously, acoustic is for the temperature measurement, but microwave we are doing for the measurement. So because we are pretty aware, there might be some minor changes in the cavity. Because of the change in the variation. And acoustic we are going to use for the speed of sound in the detect from the frequencies of several radial acoustic resonances, and K will be detected from the zero pressure limit, which is not possible. So that's why we are going to work up to 10 bar pressure, and then we will extrapolate it to the zero, and then we will calculate the value. So these are for the measurement, like these are the triplet that's required to measure, and these are the requirement for the dripping, and this work is still going on. And these are the velocity measurement for the acoustic resonator. And after the, I think most of the people who visit NPL, so the traceability pyramid, so there will be changes in the traceability pyramid. So earlier, it was based on the triple point of order, and now we can say there is a redefinition of Kelvin, then which is based on the Boltzmann constant, and then which we can do the direct realization of the primary thermometer, which is acoustic gas thermometer, and for the higher the radiation thermometer, and the 90, which is international temperature, which and provisional low temperature scale, which is defined in 2009, 2000, and then it this ITS and PLDS will be redefined uh, with some name like in the ITS some 2002, so and the realization of the fixed point, then we can do. Then for the radiation thermometry, we are having the SPRTs, capsule SPRTs, spectral radiation thermometers, and then we will do the calibration of various sensors, PRTs, RTs, thermocouples, and then IS sensor, black bodies, hygrometers, moisture, and clean thermometer in the temperature range from minus 200 degrees Celsius to 3000. So we can do the direct thermodynamic temperature measurement for the practically, and this is beneficial below 20 Kelvin to and above 1300 Kelvin, and this is the thermodynamic temperature that we like T minus T90 value will be reduce the uncertainty for the higher temperature because there is no favorable fixed point, because earlier the triple point of water was the favorable fixed point and the value was changing from there. So thank you so much for your kind attention. This one.
Thank you, ma'am. Thank you very much for this brief and wonderful presentation. Thank you very much. I would like to request all the participants to kindly switch on their videos and switch on the mic. Kindly and share the presentation, ma'am, please. Arasal and Atulji, can we make all the participants the panelists so that we can take photographs? And kindly remove the PPT, please. Kindly remove the PPT, ma'am. Kindly switch off your mic. Yes, ma'am. So I would like to request you to kindly share me this PPT so that I will share it on my website as well as in all social media platforms. The participants can be benefited at any point of time. Secondly, the video which we have recorded today will also be available on our government website. Any participant can check or can see, can get the information at any point of time with your kind permission, ma'am. Thank you. Thank you very much. I'd like to thank all the participants. Atulji, is it done? Yeah, Sanjay ji, you want to say something? Sanjay ji, someone want to say something?
आपलं येत नाही रे मला की माझं गाणं जगतो माझं
Ganesh, kindly switch off your mic, please. Whether we have taken the photographs?
I'll start video करिए.
Yes, sir. We have taken
Thank you. I would like to thank all the participants. We will meet again next week, next Saturday, with a new topic at the same time at 11 o'clock. Thank you very much. Thank you all.